Okay, so we have done area under a curve. We did it with some trapezoids. We're now going to do the area under a curve using n rectangles, right? And those are called Riemann sums, after Bernhard Riemann, who developed this. And so what we're going to do is we want to find the area under some arbitrary curve over some closed interval. So, we are going to find the area under some arbitrary curve over a closed interval. AB. He added. Care to copy that down? Comic Expo.
Joe was pretty mad.
So, we're going to draw a diagram, we're going to split it up into some rectangles, we're going to kind of examine how do we get the area of these things and the area of the whole thing.
I got it. I don't want you to.
To dirty myself?
Yes.
Appreciate it.
You deserve it.
Yeah. Okay, so let's draw ourselves a curve. There's an x and y axis. Here's some curve. Which we will call y equals f of x. And we want to get the area over some closed interval. So let's do this from A to B. And remember, when we talk about area, we're talking about a positive curve, one which is above the x-axis, and the area is the area between the curve and the x-axis. So we're going to split this curve into some rectangles. So this will be rectangle number 1. Let's draw a little area here. Here's, whoops. Control Z. There's rectangle number 2. Number 3. And I'm going to keep these widths the same. Now, technically, you don't have to, but it makes life a little bit easier if we do. And we'll go all the way along, and then at the end, we're going to end up with this last rectangle, which will be rectangle N. Okay, so that's rectangle N. I don't know if I need to shade these in or not. Okay, so what do we got here? We have N rectangles. And what we need to do is figure out, well, okay, I mean, they're not really rectangles here, right? So we need to make a rectangle. And in order to do that, we're going to use the height at the right endpoint of the interval. Okay? So we better call these things something. So let's call this x sub 0. This will be x1, x2, x3, and b is x sub n. And so we're going to do a rectangle. This is f of x1. This is f of x2, right? I'm using the right endpoint. This is f of x3, and so on, and over here. That's f of x sub n. So you can see that if we use the right endpoint, we're going to be sort of, if the curve is decreasing, we're going to be cutting off part of the curve. And, here, so we're cutting out part of the area, but here we're adding in part of the area. But the idea is we want to get these rectangles to be pretty thin, right, so that we won't be cutting out that much. And so then this distance here the width of any given rectangle is delta x. Okay, so that's a very squashed in little delta x there. Okay, so that's the width of a rectangle. So we have n rectangles. And are using the right endpoint of the rectangle to find its height. We could also use the left endpoint. We could use just any point in the interval to represent the height of the rectangle. All right, so each rectangle has a width. What's the width of any of these rectangles? What's an expression for the width? So delta x is equal to what? Gotta think back like 2 days now. B minus a over n, right? Because we're taking this whole interval whose distance is b minus a is being split into n rectangles. So each rectangle has a width of b minus a over n, right? That's the width of each rectangle. Width of each rectangle. And what we're going to say is, well, a is x sub 0. x1 is equal to x sub 0 plus delta x, right? So if I want to get to x1, I start at x0 and I go delta x over and I get to x1. x2 is equal to x1 plus delta x. x3 is equal to x2 plus delta x. And what's x sub n? Actually, we should draw a few little. Push this down a bit. Dot, dot, dot. X sub n is equal to, what's the expression? Look for a pattern. x1 is x0 plus delta x. So x sub n minus 1 plus delta x. So the area under the curve will be the sum of the area of the rectangles, right? So area So I'm using a rectangle to stand in for rectangle, so I don't write rect or rectangle or whatever, right? So the total area is the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3 up to the area of rectangle n. So we're going to squeeze in. I don't know if we can squeeze in. We'll go to another page, I think. So you got room on your page, and I'm just going to go and well, I'll give you a moment. Take a moment. Print this out. I'll pause. All right, so right underneath that, the area of rectangle 1 is the height of rectangle 1 times the width, right? Length times width. So we're using height, so it's f of x1, because that's the height of the first rectangle, times delta x. The area of rectangle 2 is f of x2 delta x. F3, rectangle 3. And we end with the area of rectangle n, which is x sub n delta x. Now, we can use summation notation to simplify this, right? Or to, I don't know, what's the word? I don't know the word. So we'll say the area is the sum of I equals 1 to n of f of x sub I delta x. So at this point, let's go back to the diagram and we'll add in the ith rectangle, right? We're just going to throw some rectangle in there and say this is the ith rectangle, and then we'll figure out, well, what's the expression for the area of the ith rectangle? Ith. So there's rectangle I, the ith rectangle. What is this? X sub I, right? Because the area of the first rectangle is x1, delta x, x2, delta x, x3. So this must be x sub I, which makes this one x sub I minus 1. Okay, so that's the ith rectangle. Where do we want to write this? Oh, let's just write it here.
Tomato special.
So the area of the ith rectangle is fx sub I delta x, which we have, right? That's the expression we have there. But what's x sub I? So we think about, right, where do you start and how many do you have to add, right? So everything starts at x sub 0. If I want to get to x3, how many delta x's am I adding? 3, right? So if I want to get to x sub I, how many delta x's am I adding? I. Okay, so f of x0 plus I delta x. That's what's going to give us f of x sub I. And then we think, well, okay, wait a sec, what's delta x? Delta x is b minus a over n. Okay, so f of x sub I, the expression for that is f of x0 plus I times delta x, which is b minus a over n. Right? So when we want to work this out for reals, then we have a formula, right? We can just substitute in the value of b, the value of a, the value of n, etc., and then we can work stuff out. But what we're going to do is make well, we're going to have a ton of rectangles, right? So the more rectangles we get, the thinner they are. And you can see the problem that happens with this where, hey, look, you cut this off. All right, well, what if it was like, this thin? Then what am I cutting off? Well, only a really tiny amount. What if it was infinitely thin or infinitesimally small, but I had infinitely many of them? And that's the idea is, right? We're going to add up infinitely many rectangles, which are infinitely small, and that will give us the actual area. Okay. And if you notice, what we did there is we did it like 5 trapezoids, and we worked it out. Okay. Now we're going to do infinitely many rectangles, right? Because rectangles are easier formula than trapezoid, right? Because this plus this over 2. Rectangle is just that. So if we have infinitely many infinitesimally small I don't think that's even spelled right. Infinitesimally is a word, but whatever. Small rectangles.
Infinite small.
Infinitesimally means really small.
It is not.
Somebody wants to Google it, we'll get the right spelling. So there's your formula for area. The limit as n approaches infinity of the sum of I equals 1 to n of f of x sub I delta x. So we're going to add up infinitely many infinitesimally small, as far as width goes, right? That's what will be infinitesimally small, is the width. Rectangles. Now this is using the right endpoint, right? Using right endpoint. You'd say, well, what if you want to use the left endpoint? Well, you can use the left endpoint. Then it becomes if we use the left endpoint, then rectangle 1 has a height of x0. Rectangle 2 has a height, go back. So if I use the left endpoint, then this I would use x0 to represent the height. And I'd use x1 for rectangle 2, and so on. And so that would give us xi minus 1 delta x. That would use the left endpoint. Okay, so you have a choice. You're saying which end of the rectangle is going to represent the height, the left end or the right end. If we choose the right end, then this number matches up with the rectangle, right? I use f of x1 to get, so I is always rectangle number. Rectangle number 1 uses f of x1 for the height. Rectangle number 2 uses f of x2. If I use the left endpoint, rectangle number 1 uses x sub 0, uses the left side for the height. But why stop there? For the little asterisk there to just say it's any number. Any number in the interval. In the ith interval. And it can vary. And it doesn't matter. Doesn't matter, none of them matter. So we're going to stick with this one. Okay. Because it kind of matches up nicely, right? I want the area of rectangle 1, I use f of x1. I want the area of rectangle n, I use f of x sub n. Okay, right endpoint. So now we do a real one. So find the area under so find the area under x squared minus x plus 3 in the closed interval from 2 to 5. I think, do I have that? Okay, so this is what the curve looks like, right? And what we're doing is calculating the area under that curve from 2 to 5. So this area, which I'm not going to shade in. All right, so where do we start? Well, we got a formula, right? Area is equal to the limit as n approaches infinity. The sum of I equals 1 to n of f of x sub I delta x. All right, what's delta x equal to? This is where we actually, now we have actual values for a and b. So 5 minus 2, because these guys are 3 units apart, divided by n. Okay, so delta x is 3 over n. So the limit so let's throw the delta x first, right? So we'll just go 3 over n times f of x sub I, right? Well, what's f of x sub I, right? We know it's f of x0, so it's 2 plus delta x, right? So it'll be 3I over n. That's how many widths, right? So when I is 1, we're going to go 2 plus 1 delta x. We'll move over to the right endpoint of the first rectangle. Okay, that's what that's going to do for us. Good, better close that bracket, right? All right, so all we're going to do is do this. Oops. Okay, well, f of x is described, right, or sorry, is defined for us here. So we're going to substitute this expression, 2 plus 3I over n, wherever we see an x in the original function definition. So we're doing the sum of 2 plus 3I over n quantity squared, right, that's the x squared, minus 2 plus 3I over n, okay, minus x plus 3. Okay, so you're adding up f of x sub I, so we have to figure what's x sub I. Okay, well you start at x0 and then you add I times the width, right? I times delta x, which was 3 over n. But we know what f is. It's defined for us. F of x is x squared. So take this input, square it, minus the input plus 3. Okay, now we get to use all of those properties of summation that we spent a little while learning. Yep.
Should that all be over n? Or just 2 plus 3i all over n? Or just 3i?
Just the 3i over n.
Who's on the second?
Better? Thank you. Y'all are doing your job. Remember, our job is turn out a good set of videos by the end of this. Just sloppy writing. Okay, so what do we got here? What do we have here? Because we got to square this in. Yeah. And pause. It's going to take a while. And we're back. Okay, so we squared this, subtracted this, added this, simplified that, and now we're ready to carry on. Okay, that 3 is a constant, right? So we know what we can do with the 3. We can move it out front, right? So it's 3 times the sum, the limit as n approaches infinity, of the sum of I equals 1 to n of, okay, so we've got 9 I squared over n cubed plus 9 I over n squared, right, because we're multiplying through the 1 over n, okay, plus 5 over n. And now, let's see, I want to take that and comment. How do I select? Control C. Control V. Okay. So it's 3 times the limit as n approaches infinity, the sum of I equals 1 to n of 9 what's the sum of I squared, right? So we look on our formula sheet, we know that there's a sum for I squared, right, which is n you're writing red. N times n plus 1 times 2n plus 1 over 6. Okay, so you see what's red here, the I squared? Well, that becomes this then, right? Because that's the formula for the sum of I squared. Plus 9 and the formula for the sum of I is n times n plus 1 over 2.
Well, this is embarrassing.
That's embarrassing.
No kidding.
Dude.
I don't even know how Firefox popped up. Very appropriate. Well, this is embarrassing. No kidding. I must have hit it. Okay.
Do you want 5 over 9?
So, let's go through and simplify, shall we?
Where'd the other end go?
Actually, you know what? Wait, I don't need this anymore, do I? I don't want that.
Where'd the other end go?
Hang on. Yeah, I'll put it in there.
Okay.
Okay, so, where do we go from here? Right, we're not doing the sum anymore, so we replace the sum, right, with these expressions. So we got 3 times limit as n approaches infinity of 9 times 1 plus 1 plus 1 over n, 2 plus 1 over n. So let's get rid of the n cubed, right?
Divide everything by that.
You know what? I'm looking at this. Let's see. Let me pause. All right, so I shall not back up the recording and explain away. I shall just explain away my embarrassing incompetence here. All right, so
Just say you found it up already.
here's what we want to do.
Human
Human too, right? Maybe bulletproof. Well, probably not either. Okay, if I divide this by n cubed and I divide the top by n cubed, but I'm going to do it a special way, right? I'm going to divide this term by n, divide this term by n, and divide this term by n, then I'm really dividing both by n cubed, right? So when I divide this term by n, I get 1. When I divide this term by n, I get 1 plus 1 over n. And when I divide this term, well, I didn't know it, so when I divide this term by n, I get 2 plus 1 over n. Okay?
What's the plus sign there?
What plus sign?
Between like the 1.
How'd you just get off the
Plus sign?
So divide this by n, divide this term by n.
We're asking about where the plus sign came from.
right there?
No, to the left. Yeah.
Oh, that's a good question.
See, that was what was confusing. I got everything out.
Oh, really? Explained it to me then. Okay, so this is good, right?
It's 9.
Divide this by n cubed.
No, it's
Oh,
9.
right. Okay, well, that's good, right?
This is good for me.
Now, we're going to divide this by n squared and divide the top by n squared, but we're going to split it up, so we divide this by n and divide this by n. And now the question comes, why is this equal to 5? Yeah, it is. Okay, so
It's a trick question.
okay, think about this. So what's this? Well, so think about this. What if we did? So what if instead of an n, we made that a 3, right? There. Let me move that over. Well. What's 5/3 plus 5/3 plus 5/3? 15/3, which is 5. 5/3 plus 5/3 plus 5/3. You got a common denominator. You add the numerators. 5 plus 5 plus 5 is 15. You need the denominator. It doesn't become a 9 or anything silly, right? So you have 15/3 is 5. So what you just think is we've got some fraction of 5 that we're adding up that many times, right? Like 5 halves plus 5 halves. Or I got 5 quarters plus 5 quarters plus, and I do that 4 times. Or I've got some infinitesimally small fraction of 5, but I'm adding it up infinitely many times as it is small, and so we just get 5.
So should it be 5 and a step above that?
Right. Should be a 5 here. There. Okay, fix that.
Oh, you actually had that before.
Yeah, I know, right? Then I panicked.
Yeah.
And my deodorant stopped working. No. My antiperspirant, I don't know. Where are we? Okay, so we're there. We're there. So that's 3 times the limit.
How are you allowed to allergies?
No. Now we get rid of the limit.
Don't you feel the sort of allergies? Like you can feel the allergies, right?
Okay, so the limit of n approaches infinity. We got a 9, we got a 1, we got a 1, we got a 0, right? 1 plus 0. Okay, 1 over n approaches infinity. We got a 2 plus 0. That's all over 6. Plus, we got a 9, we got a 1, we got a 1 plus 0. And we got a 5.
Oh, they said read down. I'm like, yeah, it was like this last month.
All right, so what do we got here? 9 times 1 times 1 times 2 is 18 over 6, plus 9 times 1 over 2, which is 9 over 2, plus 5. So what's that? 3, 4.5, 5. So it's 3 times 3 plus 4.5. That's exact, right? Like I wouldn't do that if that were thirds. Well, if that were thirds, it would be 9/3. But I wouldn't do it with thirds. It was like 10/3, but 4.5. Plus 5, 9.5, 7.5, 12.5 times 3 is 12, 36, 37.5 square units. Or units squared.
How did you go from the 6 and cubed on the bottom to just the stickers?
Oh, I'll tell you. I went and I sought the help of others. Okay, so here's what's happening here. Okay, now that it's over. I'm dividing the top and the bottom by n cubed, right? If I divide this by n cubed, we just get the 6. When I divide this by n cubed, think about it. I've got an n and an n and an n, right? So if I divide this term, so I'm not going to divide by n cubed. I'm going to divide by n times n times n, and I'm going to split it out so that each of these guys gets divided by n, right? So when I divide this term by n, I get 1. When I divide this term by n, I get 1 plus 1 over n. And when I divide this term. It took a while for me to figure that one out. Okay, I didn't figure that out. I sought help.